A Class 1 lever is set up to lift a load of 300 pounds. The fulcrum is in the middle, with the effort force exerted 10 feet from the fulcrum. The load to be moved is 3 feet from the fulcrum. What is the effort force required to move the load? Let's tackle this problem using the question strategy for numeracy. Identify, organize, set up and calculate, and decide. The goal here is to use our understanding of how levers reduce the amount of force needed to move a load in order to determine how much effort force will be needed for the job. Your first step is to identify what you need and what you already know. Let's start by identifying what you need. The effort force required to move the load. Now, what do you know? You know the load weight in pounds, as well as the effort distance in feet. You also know the load distance, also in feet. Let's underline those numbers in the question. Your next step is to organize your information and choose a formula. Drawing a picture can really help, especially in this case. It will help you clarify your values and how everything works together. Let's keep it simple. Make a triangle and use downward arrows for load and effort. Use the fulcrum to separate the load information from the effort information. Place the load distance on the same side as the load and the effort distance on the same side as the effort force. Because we are dealing with load weight, load distance, effort, and effort distance, we're going to use the lever formula. L times LD equals E times ED. Before setting up our equation, let's start by reviewing what the symbols in the formula mean. L stands for load weight, measured in pounds. LD stands for load distance, measured in feet. E stands for effort, also measured in pounds. And ED stands for effort distance, also measured in feet. The lever formula is based on the law of conservation of energy, which states that energy cannot be created or destroyed, only transformed from one form to another, or transferred from one object to another. That means that the work we get out of the lever is equal to the work we put into it. Using the lever reduces the input force needed to move the load, but there is a price to pay. We will need to exert that input force over a longer distance. You can see this relationship in the formula because the product of the load weight and load distance is equal to the product of the effort and effort distance. Now it's time to set up your equation and calculate. Start by checking to make sure your values are in the right units. Looks like you're good to go. Go ahead and drop those numbers into your formula. Use your calculator to get the answer. You'll want to get the variable E alone on one side of the equation. That means moving the 10 over to the left side, but there's a trick to getting it right. To do that, you'll have to get rid of it on the right to balance out the equation. But how? Here's your clue. See this multiplication symbol? To clear the right side, just use the opposite operation. What's the opposite of multiplication? Division. So, divide both sides by 10. Go ahead and use your calculator one more time. There. It appears the effort force needed to move the load is 90 pounds. Now for the final step, deciding if your answer is correct. Let's reread the question and make sure we've covered all of our bases. First, did we calculate what we needed? Yes. Second, did we take all of the keywords and information into consideration? Yes. There's just one question left to ask. Is our answer reasonable? Does it make sense based on the type of answer we should get? The lever formula is like a balance. You can use less force to move a load if you exert it over a longer distance. The effort force we calculated is less than the load and is exerted over a greater distance. So, it appears our answer is not only mathematically correct, it's also reasonable. And there you have it. Great work! Mastering any new skill takes time and application. It also means getting the job done right and keeping everyone safe. You've got this.